Alright, so Vachavadi, we are going to start with this new chapter of magnetism and matter, in which we are specifically going to discuss about certain things like what is magnetism, what are the properties of magnetism. Here and there we will discuss as to when and how magnets were discovered, then what is the Earth's magnetic field, what is the angle of dip, and so on and so forth. More of a theoretical chapter. We will see what are the similarities there with electricity or electrostatics for magnetism. Okay, so let's start with this. Okay. So when was magnetism basically discovered? So it was way back in Greece at around 600 BC. Magnesia, the name of this place was Magnesia in Greece. At around 600 BC, some shepherds accidentally discovered magnets. So this was more or less an accidental discovery. Later, Chinese found that the magnets possess property to show direction. So they started using it in navigation tools. So when we suspend a compass needle or magnetic compass, it always adjusts itself in the north-south direction. Still we use it, okay? But it was the Chinese who first started using it because of the fact that it had directional properties, okay? All right. So this was a little history about it. Now we know that when we place like poles in front of each other, north or south poles, obviously it will be repulsion. Very much similar to the force which is experienced when two plus charges or two positive charges are placed together. When we place unlike poles in front of each other, they will experience an attractive force, very much similar to the two charges which are placed, which are opposite, plus or minus, that they experience. But we can say that magnetism, repulsion is a short test of magnetism. So if we know that there is a magnet, and if we bring another magnetic object near to it, obviously it will experience an attractive force only. But if we happen to bring a magnet near it, then it will experience both attractive as well as repulsive force if we happen to change the polarities. Okay, so these are certain things that we have studied in earlier classes. If we take a bar magnet and if we sprinkle some iron dust, we will see that the iron dust or the iron particles basically arrange themselves in these types of rings. So an electrical charge produces electric field, just as an electric charge produces an electric field around it. A magnet will also produce magnetic field around it. As an electric charge produces electric field in its surroundings region, a magnet also produces a field known as magnetic field in its surrounding region. As early as 6th century BC, the Greeks had some knowledge of natural magnets. Thales of Miletus knew that pieces of a naturally occurring iron ore lodestone or magnetite or black iron oxide had the property of attracting small pieces of iron. Okay, the word magnetism originates from the place Magnesia, a province in the upper part of Greece where this ore was found. So this was basically found in Greece, as we have already discussed. Later on, the Chinese discovered that thin long pieces of lodestone, if suspended horizontally and freely with a string, would naturally orient roughly in the geographical north-south direction. So that's when, for navigation purposes or for people who are going into the sea to see directions, they started arranging themselves. In fact, the word lodestone means a leading stone which expresses this directional property valuable to travelers. By about 1000 AD, the Chinese were using the magnetic compass for navigation. It was William Gilbert who, in his book The Magnet of 1600, first suggested that the earth itself was a huge magnet, causing the alignment of compass needles. So this was the first time that it was actually suggested that the earth itself is a huge magnet. So that's how the magnetism was actually discovered. So what are the basic properties of magnets? We are very much aware of these things. It's just that it's just a brush up of the knowledge that you have already acquired in your previous standards. So first is the attractive property. A magnet attracts small pieces of iron, cobalt and nickel. Iron, cobalt and nickel happen to be the magnetic materials. So if we place a bar magnet, you will see that the maximum amount of magnetic particles actually arrange and align themselves around the poles. Okay, a magnet attracts small pieces of these. When a magnet is brought near a heap of iron fillings, the ends of the magnet show the greatest attraction. So we can say that the poles actually show the greatest attraction. The magnetism is strongest around the poles. These ends where the magnetic attraction is maximum are called the poles of the magnet. Thus, every magnet has got two poles. So every magnet will actually have two poles. Directive property, when you happen to suspend a magnet When a magnet is suspended or pivoted freely, it aligns itself in the geographical north-south direction. It will align itself in the geographical north-south direction. The pole of the magnet which points towards the geographic north is called the north-seeking pole. The other pole which points towards the geographical south is called the south-seeking pole of the magnet. So when you suspend a magnet, it actually aligns itself along the geographical north-south direction. Okay, so that's how poles are. Like poles repel and unlike poles attract. If the north pole of a magnet is brought near the north pole of a suspended bar magnet, the poles are found to repel each other. So these poles are basically repelling each other. Okay, so we have seen this. Like two south poles also repel each other. In contrast, north and south poles always attract each other. So if we place like poles in front of each other, they will attract. If we they will repulse. I'm so sorry. And repulsion is a sure test for magnetism. Okay, if you are bringing in one magnet and another magnet at one point of time, or by changing the poles, you will observe the repulsive property. So the moment the other object shows repulsion, it has to be a magnet. Okay, so these are basically this action can be described by the law of magnetic poles, which states, so what is law of magnetic poles? That magnetic poles repel, like magnetic poles repel, and unlike magnetic poles attract each other. So these are some things which we have already seen. Okay, in dipoles, electric dipoles, if you happen to separate one charge or isolate one charge, the other charge will still exist. So electric monopole has its existence. However, magnetic monopole doesn't exist. Magnets will always exist in poles. So if you happen to cut a magnet in between, it will reorganize and readjust itself to north-south. Again, if you happen to cut it again, no matter how many times you cut a magnet, it will always have a north and a corresponding south pole. So magnetic monopoles do not exist. They will always exist in dipoles. So a north pole will have a corresponding south pole and vice versa. Okay. So if we try to isolate the two poles of a magnet from each other by breaking the magnet in the middle, each broken part is found to be a magnet with north and south poles at its ends. If we break these parts further, each part again is found to be a magnet. So unlike electric charges, magnetic monopoles do not exist. Every magnet exists as a dipole. So all the magnets will actually exist as a dipole. This will be there. Magnetic induction. Now what is magnetic induction? So let's say we have a magnet here which has got north-south pole, and we happen to bring an iron piece. So the iron piece gets attached to it by the property of magnetism. Now to this iron piece, if we bring another piece, so this will also, so long as the iron is actually attached to a magnet, it will itself behave like a magnet. This is called magnetic induction. So magnetic materials, the moment they are in contact with a magnet, start behaving like a magnet. So a magnet induces magnetism in a magnetic substance, and magnetic substances primarily we know are iron, cobalt and nickel. Okay, placed near it, this phenomena is called magnetic induction. When north pole of a powerful magnet is placed close to a soft iron bar, the closer end of the bar becomes south pole and the further end becomes the north pole. So the moment a bar is basically attached to a magnetic bar, an iron bar, it also starts behaving like a magnet. As a result, the magnet attracts the iron bar. This induction precedes attraction. Okay, this induction precedes attraction. Repulsion is a surer test of magnetism, as I have pointed out earlier. A magnet can attract another magnet. Also, it can attract. So attraction is a property which a magnet shows for another magnet as well as for magnetic substances. But repulsion is a property which a magnet will show only for another magnet, not for other magnetic substances. So if you happen to bring an object close to a magnet and it experiences a repulsive force, then the other object definitely is a magnet. So a magnet can attract another magnet. Also, it can attract magnetic substances like iron, nickel, cobalt, etc. However, a magnet can repel another magnet only. So repulsion is a surer test for magnetism. This generally is a sure test for magnetism. Okay, so these are some important things that we have to consider. Magnetic field. So wherever the magnetism around a magnet can be felt, that is known as the magnetic field. The space around a magnet which its influence can be experienced is called the magnetic field. So the entire space which is there around a magnet in which its magnetic field can be felt is called the magnetic field. Uniform magnetic field. A magnetic field in a region is said to be uniform. It has some magnitude and direction at all points of the region. So same magnitude and direction, we will call it as an uniform magnetic field. Is there a non-uniform magnetic field? Yes. So let's say this is a current carrying wire. If we happen to distance ourselves, so a current carrying wire will have a magnetic field around it. If we happen to increase this distance, the magnetic field is going to reduce. So that is called a non-uniform magnetic field. However, between two magnets or between the two opposite poles of a magnet, you will always have a uniform magnetic field. So a magnetic field in a region is said to be uniform if it has same magnitude and direction at all points in the region. At a given place, the magnetic field of Earth can be considered as uniform. The field due to a bar magnet is not uniform. Okay. A uniform magnetic field acting in a plane of a paper. So this is something that is important. So acting in the plane of a paper is represented by parallel lines. So if let's say this is the plane of the paper and we have a north pole and a south pole, so the magnetic fields will be directed like this. And these are parallel lines, equidistant parallel lines. Uniform magnetic field means equidistant parallel lines. If I happen to represent it other ways, okay, let's say if I am representing parallel lines, but I am representing parallel lines like this. So this is, let's say, one line, this is one line close, this is a little further, this is a little further, and this is far further. So if you see that the lines are parallel but not equidistant, so this will represent the direction. However, it also represents that the field is not uniform. If the field is uniform, then the distances between these parallel lines is going to be the same, equidistant. Okay. So uniform magnetic field acting in a plane of paper is represented by equidistant parallel lines. So it's important that it is represented by equidistant parallel lines. This is represented by equidistant parallel lines. A uniform magnetic field acting perpendicular to the paper and directed outwards is represented by dots. Perpendicular to the paper and directed outwards towards you. Okay, so this is the paper towards me. This will be represented by dots. So this is a uniform magnetic field. How do we know it's a uniform magnetic field? Between all these, the distances are the same. If you happen to join 4 points, you will get a square. So it is towards you, it is away from you. A magnetic field which is parallel is represented by these lines, or rather a magnetic field which is in the plane of the board is represented by these lines. A magnetic field which is coming out is represented by these dots. A magnetic field which is going inside is represented by these crosses. Okay, by dots. A uniform magnetic field acting perpendicular to the plane of the paper and directed inwards, so this is basically inwards, is represented by crosses. A uniform magnetic field acting perpendicular to the plane of the paper and directed towards you is represented by these dots. Okay, now magnetic poles, very important. Okay, magnetic poles, these are regions apparently concentrated magnetic strength. So magnetic poles are basically the two ends of a magnet where the strength of the magnetic field is the highest. Okay, so when you take a bar magnet and you happen to sprinkle some iron dust, you will see that the maximum number of iron dust or iron fillings get attached to the poles. So obviously this happens because the poles have the highest strength. So these are regions of apparently concentrated magnetic strength in a magnet where the magnetic attraction is maximum. The poles of a magnet lie somewhat inside the magnet. So if you see, the poles of the magnet are not at the ends. We will see the last concept here, magnetic length, which is associated with it. So the poles of the magnet are not actually at the direct ends. They are somewhat inside. So the north and south pole of a bar magnet will not be at its geometrical ends. It will be somewhere inside. Okay. So this is basically the magnetic axis. The line which connects the north or south poles is known as the magnetic axis. This is basically a bar magnet. So what is a magnetic axis? The line passing through the poles of a magnet is called the magnetic axis of the magnet. This is known as the magnetic axis of the magnet. Magnetic equator. What is magnetic equator? A line passing through the center of the magnet and at right angles to the magnetic axis is called the magnetic equator of the magnet. I'm sorry. So this will be the magnetic equator. It is perpendicular to the magnetic axis and passes through the center. The line passing through the center of the magnet and at right angles to the magnetic axis is called the magnetic equator of the magnet. Magnetic length, this is very important, bacha body. The distance between the two poles of a magnet is called the magnetic length of the magnet. So this is basically the distance between two poles. The poles are not at the ends. So the geometric length will be greater than the magnetic length. The geometric length of a magnet will always be greater than the magnetic length. So it is found that magnetic length upon geometric length has a ratio of 0.84 in a bar magnet. So the distance between two poles of a magnet is called the magnetic length of the magnet. It is slightly less than the geometrical length of the magnet. And if you see, for any bar magnet, the magnetic length upon geometric length is going to give you a number of 0.84. Okay, so this is basically the magnetic length upon geometric length. Okay, Coulomb's law. So what is Coulomb's law of magnetism? Very much similar to the Coulomb's law of electrostatics. So what does Coulomb's law of electrostatics say? That the force between two charges, that is Q1 and Q2, is equal to what? Directly proportional to the product of the charges. The force is inversely proportional to the square of the distance between the two charges. So the force is equal to K Q1 Q2 upon R square. That is what is proposed by Coulomb's law. Okay, so Coulomb's law of magnetic force, this law states that the force of attraction or repulsion between two magnetic poles is directly proportional to the product of their pole strengths and inversely proportional to the square of the distance between them. So this is how Coulomb's law of magnetism is represented. Force is directly proportional to Q1 Q2 upon R square, which can be said that force is equal to K, which is basically a constant. We will see that the value of this K is mu naught by 4 pi. In electrostatics, so it's almost the same. So if you see in electrostatics, the same Coulomb's law is F is equal to K Q1 Q2 by R square. So Q1 and Q2 are basically charges, and R is the distance between these charges. R is basically the distance between distance between these charges. Okay, so here F is equal to, this K is how much? 1 by 4 pi epsilon naught Q1 Q2 by R square. 1 by 4 pi epsilon naught, we all know, has a value of 9 into 10 raised to 9. Okay, that's a numerical value. In the same way for magnetism, if Qm is basically what? The pole strength. Let's say Qm1 is the pole strength of one magnet and Qm2 is the pole strength of another magnet. So we can say that the force of attraction or repulsion, depending on whether it is not, so the force will be equal to K Qm1 Qm2 by R square. So that will be mu naught by 4 pi Qm1 Qm2 by R square. That will be, so this is basically pole strength and this is the distance between them. Mu naught by 4 pi has a value of 10 raised to minus 7. Mu naught by 4 pi. So just as 1 by 4 pi epsilon naught has a numerical value of 9 into 10 raised to 9. In the same way, mu naught by 4 pi has a numerical value of 10 raised to minus 7. Mu naught is known as permeability of free space. Epsilon naught is known as permittivity of free space. Okay. So not some things that you have to rack your brains on. All you need to remember is that the Coulomb's law is pretty much applicable in the same way for magnetism as it is applicable in electrostatics. Okay. Okay, so here we have Q1. Okay, so mu naught by 4 pi Qm1 Q2. So where K is a proportionality constant which depends, this proportionality constant depends upon the nature of the medium as well as the system of units chosen. So when it is basically SI units chosen and the poles are in vacuum, SI units and poles are in vacuum, then it will be F is equal to mu naught by 4 pi Qm1 into Qm2 by R square, where mu naught is the permeability of free space and is equal to 4 pi into 10 raised to minus 7. The unit is Henry per meter. We can define unit magnetic form in the form of Coulomb's law. So let's say if the pole strength is taken as 1 unit and the distance between the poles is taken to be 1 meters, then mu naught by F will be equal to, obviously what? This is 1, this is 1 and this is 1. So F will be equal to mu naught by 4 pi. Hence, a unit of magnetic pole may be defined as the pole which when placed in vacuum, a unit of magnetic pole placed in vacuum at a distance of 1 meter from an identical pole. A unit of magnetic pole can be defined as when it is placed in vacuum from another unit magnetic pole by a distance of 1 meter, experiences a force of 10 raised to minus 7 Newton. Experiences a force of 10 raised to minus 7 Newton. That's how you can basically define magnetic pole strength. Okay, so here we have the magnetic field lines are a visual and intuitive realization of the magnetic field. Okay, outside the magnet, the field is directed from the north pole to south pole. Very important. Outside the magnet, it is directed from north pole to south pole. Inside the magnet, it is directed from south pole to north pole. So what are the properties of magnetic field lines, Bachawadi? magnetic field lines form closed loops. So these are basically forming closed loops, and at any point of time the tangent which is drawn will give the direction of the magnetic field. So here it is originating from north pole and terminating at the south pole. If at this point I happen to draw a tangent, the direction of the tangent is the direction of the magnetic field at that point. Again, the direction of the tangent is the direction of magnetic field at that point. Again, here it is going from north to south pole. So the direction of the tangent will give the direction of the magnetic field at that point. Okay. So magnetic field lines form closed loops. The tangent to the field line at a given point represents the direction of the net magnetic field at that point. Closer the field line, stronger is the magnetic field. So if you see that near the poles, the field lines are very much closer. So closer the field lines, stronger is the magnetic field. The more closer the field lines are, the more stronger will be the magnetic field that is experienced. Magnetic field lines never intersect each other. So they will never intersect each other, because if they happen to intersect each other, let's say taking a hypothetical case in which two magnetic field lines are intersecting each other. Obviously, if we happen to draw a tangent here, the direction is this way. If we happen to draw a tangent here, the direction is this way. Okay. So magnetic field lines never intersect each other, because at the intersection there will be two tangents giving two different directions of the field, which is impossible. Okay. A magnetic line of force may be defined as the curve, the tangent to which at any point gives the direction of the magnetic field at that point. It may also be defined as the path along which a unit north pole will tend to move if free to do so. So what are properties of magnetic lines of force? Magnetic lines of force are closed curves which start in the air from the north pole and end at the south pole. Please pay attention. These are closed curves. The second thing is north pole to south pole in air. So in air, they will always be directed from north pole to south pole and then return to north pole through the interior of the magnet. Within the magnet, it is from south to north pole. So direction of lines of force in air will be from north to south pole, and within the magnet it will be from south to north pole. Okay. The lines of force never cross each other. They will never cross each other. If they do so, that would mean that there are two directions of the magnetic field at the point of intersection, which of course is impossible. They start from one end and end on the surface of the magnet normally. The lines of force have a tendency to contract lengthwise and expand sidewise. This explains the attraction between unlike poles and repulsion between like poles. The relative closeness of the lines of force gives a measure of the strength of the magnetic field, which is maximum at the poles. So at the poles, they are very close together, and that's the reason the strength of the magnetic field is maximum near the poles. Okay. Plotting a magnetic field. The magnetic field around a magnet can be traced with the help of a magnetic compass needle. If you happen to basically take a compass needle, okay, this is basically a compass needle which always will arrange itself along the direction of external magnetic field. So the magnetic field around a magnet can be traced with the help of a magnetic compass needle. It consists of small and light magnetic needle pivoted at the center of a small circular brass case provided with a glass top as shown. The north pole of the magnetic needle is generally painted black or red. So this is basically the black or red. If I happen to arrange this, this is how it is going to look. Okay. So from the north to the south pole, this is the magnetic field of a bar magnet with a compass needle. To plot the magnetic field of a magnet, the magnet north-south is placed on a white paper. The compass needle is placed near the north pole. The positions of the two ends, south and north of the needle, are marked by pencil dots. They are basically marked by pencil dots. These are marked by pencil dots on the paper. The needle is now displaced to the new position so that its south pole exactly comes over the mark previously. So if you happen to plot this, by joining all these dots, you will actually get the magnetic field around a magnet in air. Magnetic dipole. In electricity, the fundamental or simplest structure that can exist is a point charge. Here, two equal and opposite charges separated by a small distance constitute an electric dipole. So let's say in electricity, we will have, let's say this is plus Q charge and this is minus Q charge. They are separated by a certain amount of distance. This is basically what? An electric dipole. In the same way, we have QM and QM. These are basically north and south. So this is basically north and this is basically south. This will constitute a magnetic dipole. This will make a magnetic dipole. Okay. Which is described by an electric dipole moment P. In magnetism, isolated magnetic poles do not exist. So this is very important. In magnetism, isolated magnetic poles will not exist. There will be no monopoles. No magnetic monopoles are possible. Okay, here the simple structure that can exist is the magnetic dipole. Electric monopoles can exist. So if I happen to take or isolate this charge, this can exist independently. However, if I happen to take off one of the pole strengths, it will not exist. So magnetic monopoles do not exist. Electric monopoles can exist, which is described by a magnetic dipole moment. The arrangement of two equal and opposite magnetic poles separated by a small distance is called a magnetic dipole. So let's say this is QM, this is QM, separated by a small distance R. This is basically a magnetic dipole. This happens to be a magnetic dipole. Just give me a moment here. Okay, so every bar magnet is a magnetic dipole. Every bar magnet will behave as a magnetic dipole. A current carrying loop behaves as a magnetic dipole. If there is a current carrying loop, it will also behave as a magnetic dipole. So let's say this is basically a current carrying loop. This will behave as a magnetic dipole. One end will be behaving as a north pole, the other end will be behaving as a south pole. Okay, if there is current which is passing through the loop, one end will behave as a north pole, the other end will behave as a south pole. A current carrying loop behaves as a magnetic dipole. Even an atom acts as a magnetic dipole. Why? Because in an atom the electrons are revolving. So this is basically a moving charge. A moving charge creates magnetism due to the circulatory motion of the electrons around its nucleus. So magnetic dipole moment. Now what is magnetic dipole moment? The magnetic dipole moment of a magnetic dipole is defined as the product of its pole strength. This is pole strength. It is a vector quantity directed from south pole to north pole. This L vector is always directed inside a magnet from south to north pole. So if we have a magnet like this and this happens to be the magnetic length, for calculation purposes we are taking this to be 2L. Understand this? We can, this 2L doesn't matter. Okay, let's say if it is given as 4 meters, so this 2L means 4 meters. We will have to take this 4 meters as a length. The 2L is just taken for calculation purposes. We will see that in order to calculate the magnetic field at axial point or on the equatorial point, we will have to bifurcate is just L, so that the two ends are having L and L. So QM, so let's say this distance between, so we know that the magnetic length is slightly lesser than the geometric length. Let's say the magnetic length of a magnet happens to be 12 and the pole strength is QM. So the magnetic moment here will be how much? This will be QM into 2L. Very important. If this happens to be the north pole and this happens to be the south pole, the magnetic moment will be directed along the magnetic field inside the bar magnet. And we know that in air, the magnetic field is from north to south pole. However, inside the magnet, it is from south to north pole. Okay. So where QM is the pole strength and 2L is the magnetic length of the dipole measured in south to north pole. Okay, we shall see later on that the SI unit of magnetic dipole moment is Ampere meter square. This is Ampere meter square. Magnetic dipole, the SI unit is Ampere meter square, or we can say joules per Tesla. So these are the units, SI units of magnetic moment. So what is magnetic moment? The product of the pole strength and the length vector, that is the magnetic length directed from south to north pole. Okay, don't get confused by this 2L. Whatever is given as the magnetic length, that will be the length. So let's say if the length is given as 4 meters, you would not take it to be 8 meters. Okay, you would keep it as 4 meters only. Okay, this 2L is generally taken for, just as we have in electric dipole. Electric dipole also, in electric dipole also it is Q into 2L. Okay, in the same way here also is the same thing. It's the same thing. Okay, so this is basically magnetic dipole. Okay. So what is magnetic dipole moment, bacha party? That will be M. That is magnetic dipole moment is M is equal to Q into 2L. Coulomb's law is what? Force. So just a recap of what we have studied. Mu naught by 4 pi Qm1 by into Qm2 by R square. The pole strength is in ammeter meter. Force is in Newton. Distance is in meter. So mu naught will be 4 pi into 10 raised to minus 7. And this is basically Tesla meter per ammeter. This is mu naught. Okay. So this is something that is concerning with magnetism. We will do some numericals to have a clearer concept of these things. Okay.